Lab 5, we are focusing on a slinky drop. So the purpose of this lab is to predict the motion of a spring as it is dropped from rest. And in our results, we find that the top of the spring falls and our model closely matches our video analysis, and the bottom will remain stationary in both analyses. So the models and principles that we use a tracker model, the glow script model, Newton's second law, our momentum principle, the concept of drag, and within Newton's second law, we're looking at two main forces, or actually three main forces, the force of gravity, for spring force, and our drag force. And so some assumptions we made, a lot of the spring variables are found online because we didn't create the video that we're analyzing, and drag is a dropping effect affecting the drop, and that our camera does not suffer from parallax error. And so some equations we used are F net divided by mass equals acceleration. We used our velocity update equation as well as our position update equation, force of gravity, force of drag, and our spring force. And so some initial conditions, we determined that Derek's height is 1.75 meters, our spring's mass is 0.218 kilograms, the number of coils is 98, radius is 0.035 meters, and the spring constant is 0.82 newtons per meter. And then our camera does not move position, the drag coefficient is 0.175, and the camera FPS is 300. So in the video, we see that a spring is dropped from rest in static equilibrium. The top of the spring moves while the bottom doesn't before they join together and falling to the ground. At static equilibrium, the force of gravity and the spring force are the net force. And so in our glow script code, we do the same thing. We give the spring initial stretch and forces from the tracker video. Then we update the spring and drag forces, as well as update the velocity and position of the top of the spring. And so in here, you can see all of our constants here, as well as what we use to update the spring. We have our initial conditions, and then we define our forces, and then we update our force, update our velocity and position, and then we run this, and you can see that the top of the spring falls to the bottom, and then after that they'll fall together. And so we can go on and compare the data that we got from both the tracker and the model, and you can see that we both end up in the relatively same position, and they both begin very similarly in falling, and then our tracker kind of goes down much faster, but almost at a similar rate. It just has one major drop. And so some errors that could have occurred in this, where the tracker video could have had parallax error as we were not in control of the video, and there's motion blur occurring in the video, causing it to be difficult to track exact points at times. And then some constants may not have been accurate as I couldn't measure everything myself. I was relying on the internet to be able to find the mass and the spring constant and things like that. And so our reasoning and conclusions, we found that there has to be some internal tension force of spring up from the spring, causing the bottom to stay stationary, and that must counteract gravity in that point. And then our glow script model pretty accurately predicts reality despite differences in the models. And so this means, so the bottom remains stationary because there's a tension force pulling up on the bottom of the spring that doesn't go away until the slinky collapses. And if the slinky was dropped in a vacuum, eliminating air resistance, the gravity would still cancel out the tension force created by the spring suspension, thus the same motion would occur. We would just see it fall faster once the top reaches the bottom, causing the collapse.